10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Hi everyone. So what are we going to discuss today? So today we are going to discuss on electric field. So what is electric field? And an electric charge produces an electric field in the surrounding space. So when another charge is brought in this region of space, it experiences an electric force. So it is not charge which exert the force, but it is the field of a charge due to which another charge experiences an electric force. So thus, an electric field said to be exist in the region if another charge experiences an electric force in that region. Okay, example, look at this simple experiment. Okay. So this is electric field area. This is two electrode, okay, positive and negative. So this is let's say we use a seed, of a grass. Okay, we put here. So for the when there is existence of the electric field, so you can see that the seeds arrange themselves like this. Okay, so this is to show simple experiment to show the existence of the electric field. Okay, this is another region, okay, by the circular electrode here. One is positive and another one is negative. Okay, cathode and anode here. Okay, so to show the existence of the electric field, so we draw it using a line, and the direction of the electric field is shown by the arrow. So this one you've learned in the Form 1, Form 2, Form 3. If this is a positive charge, so the electric field direction is radially outward. Okay, and if the charge is a negative, this is a point charge. We call this a point charge. So if for point charge, the region, the electric field direction is radially inward. Okay, so when you draw, you must make sure it is drawn equally spaced between each other. Okay, like this one. Okay, so if there are two charges, one is positive, one is negative, so the electric field shown how to represent in the drawing, like in your drawing, the electric field. So you draw like this. Okay, this is for the two equal magnitude of charge. Okay, so the charge is in coulomb unit. Okay, if they have two equal charge, so this is the region shown. How you must know how to draw the electric field. Okay, don't forget to put the arrow to represent the direction of the electric field. So the direction of the electric field is from positive charge to negative charge. Okay, so it's just like similar to the magnet, by the magnet. Okay, region by the magnet. This is magnet. Okay, the region shows by the dust, iron dust. Okay, here this one similar to this. Okay, for the like charges, like this one, positive or negative. So this is the pattern. Okay, the electric field pattern. Okay, if the charge is not the same, okay, let's say one is negative Q, one is positive 2Q. Okay, so the shape is different. So you've learned before in Form 1, Form 2, Form 3, the region is for two, shown here is for the two similar charge. If this one is negative, a positive Q, this is negative Q. But if it is one is negative Q, the other one is positive 2Q coulomb. Okay, the force, this one means the force is larger. The electrostatic force is larger, so the shape will become like this. Okay, so the crowded, you see that the line here looks crowded, right? So that's mean the electric field here is larger compared to the electric field on this side. Okay. Okay, so this is another examples of the electric field lines pattern. Okay, for the object with unequal amount of charge. For unequal amounts of charge. So many students are confused with these two, with this the pattern. When the charge, like the two charges, same magnitude or different magnitude. So you must know how to distinguish between the two pattern of electric field. Okay, another one is if the parallel plate, we use parallel plate. Just now is point charge. This one is the parallel plate with charge positive Q. Another one is negative Q. So how you draw the pattern? The electric field pattern is drawn like this. And make sure it is equally spaced between each other. Okay, on the top here, it's slightly bent. The line here slightly bent. But you don't you draw straight line also is okay. Okay, so the electric field between two closely spaced oppositely charged parallel plates is constant. So that's why you must draw all these lines equally spaced with each other. Okay, and the direction is from positive plate to negative plate. Okay. So this is example, okay, animation to show the direction of the direction of electric field and also the strength of the electric field. Okay, we skip this. Okay, so to derive electric field strength, we use the equation here, E equals to F per Q. Okay, so what is the electric field strength? So electric field strength is the force on a small charge divided by the charge. Okay, this is electric field strength. So the force divided by Q. So this Q is called a test charge. Okay, and it's usually positive charge. Okay, so if this is okay, we go to the next one. Next one. Okay, if this is a charge, if this is a point charge, with value positive Q, capital letter. Okay, we use capital letter, and then we have the direction, like we discussed just now, is this way. Radially outward of the point charge, but we just draw one only. Okay, one line, but actually it's surrounding, radially outward from this charge. Okay, let's say this is one line of electric field to represent the electric field along here, and then symbol use E for electric field. Okay, this is a test charge, positive Q. So if this test charge we put here, so what happened? This charge will experience a force. If no charge here, we don't know whether it has electric field or not in that region. Okay, so if we put a test charge, then we know that if this charge experience repulsion force, because positive, right? So the direction of electric field is this way, because direction of electric field followed the direction of the force. Okay, so if the force, if this positive charge is a test charge, always positive charge. So if that's mean if we put here positive charge and the source of charge here is negative, then the direction of electric field will be opposite, because this positive test charge will attract to the negative charge here. Okay. Okay, so now we use this one. So given from the definition of electric field equals to F per Q. Okay, we use this definition from the electric field. Then let's say the distance between them is R. So you substitute using the Coulomb's law. So you substitute the Coulomb's law here, QQ, okay, per 4 pi epsilon naught R squared. Substitute into here. Okay, what we get? We can cancel the Q. That's why this is called a positive test charge. We call this test charge because we can cancel the test charge magnitude already. So cancel this Q, so we get the formula for electric field. So this is the derivation process of electric field Q. So electric field for this Q, okay, this yellow point charge here, Q. Okay, the electric field here is Q per 4 pi epsilon naught R squared. So the test charge with value for small letter positive Q actually not in use. Okay, so memorize this formula for the electric field. Okay, this is like I said just now, if negative charge, if this is negative charge, so if we put a test charge positive charge here, what happened? It will attract to the negative charge here. So if this test charge experience attraction force, okay, attract to the charge here. So that's mean direction of F this way. So direction of E also this way. Okay, direction of E also this way. So that's mean it's radially inward. Okay, radially inward. So that's why for the point charge, negative charge, the direction of electric field is radially inward. Okay, it's follow the direction of the force experienced by the test charge. Okay, so now using the definition of electric field, E equals to F per Q. The distance is, let's say, R between them. So using Coulomb's law, and we substitute into here because this is negative, this is positive, so negative, bring along the negative. Okay, so we get this equation, cancel out Q because Q is a test charge. So that's why it's called test charge because we don't need the magnitude. So we get the E equals to negative Q per 4 pi epsilon naught R squared. So this means that for the negative point charge, the direction of electric field is radially inward, given by the negative here. Okay, so let's try this example. A point charge with a mass of 1.40 kilogram and charge of 250 microcoulomb is placed into a constant electric field. If the strength of the electric field is 863 Newton per coulomb pointing due north, so what is the force on the charged particle? Okay, so using the F equals to QE from the E equals to F per Q, cross multiply, so we get QE. So you substitute this electric field and then the electric field, okay, 863 Newton per coulomb. This is the unit for electric field, Newton per coulomb, because force is Newton, Q is coulomb, so Newton per coulomb is unit for the electric field. Okay, and then the charge is given 25 microcoulomb, so convert to coulomb. So we get the force 21.6 Newton. Okay, very simple, this example. Okay, so since the charge is interacting with the electric field is positive, so the force also points north, okay, same as the electric field. So the direction of electric field is same as the force. Okay. Okay, now we go to the example, next example. What is the strength and direction of electric field? 3.74 centimeter on the left hand side of a 9.1 microcoulomb negative charge. Okay, so from E equals to Q per 4 pi epsilon naught R squared. Okay, you substitute the value of 1 per 4 pi epsilon naught, which is 8.99 actually, 8.99 times 10 to the power of 9. And then the charge 9.1 microcoulomb convert to coulomb, and the R is distance 3.74 convert to meter squared. So we get electric field 5.9 times 10 to the power of 7 Newton per coulomb. So we use the formula of electric field that we derived just now, Q equals to 4 pi epsilon naught R squared. Okay, so the direction is to the right, because let's say this is the electric, this is a negative charge 9.1 microcoulomb, so the direction is radially inward. Just draw one of the electric field line. So 3.74 centimeter on the left hand side. Okay, so that's why it's to the right. Okay, now we go to another example. At what distance from a negative charge of 5.536 nanocoulomb would the electric field strength be 1.90 times 10 to the power of 5 Newton per coulomb? So using the formula E equals to Q per 4 pi epsilon naught R squared. So you substitute all the value given, values given. Okay, Q nanocoulomb is to convert to coulomb becomes times 10 to the power of negative 9. Okay, distance. Okay, we want R, right? So just cross multiply, substitute the electric field strength. So you get the R is 1.6194 times 10 to the power of negative 2 meter. Okay, the question is 1 R, right? So you just rearrange the equation to get R. Okay, very simple. Okay, now if it involves two charges, so how to find the electric field? Okay, to find the electric field, given that okay, we read the question first. Find the magnitude and direction of the electric field strength at the point P due to the point charges at A and B as shown in the figure. Okay, A, B. Positive 2 microcoulomb and negative 8 microcoulomb. Okay, so distance here from point P is 10 centimeter, here also 10 centimeter. So for positive charge, the direction of electric field is radially outward. We just draw one line joining the line AP. So you draw one line only for the electric field. Okay, because we want this at this position. So electric field is radially out from the positive charge here. So you draw. So you just draw from point P here, name as E1. You do the same for negative charge. Negative charge, the direction of electric field is radially inward. If radially inward, so you just draw one line only comes from this P. So you name this as E2. Okay, so this is electric field experienced by the, if you put a charge here, okay, so that test charge will experience force by these two, by these two A, B charge. The direction is E1 and E2. Okay, after you determine the direction of E1 and E2, okay, then we calculate E1 and E2. So using the formula Q per 4 pi epsilon naught R squared. So E1 is because of this charge. So you substitute 2 microcoulomb. Okay, distance is 10 centimeter convert to meter. So you get this value. Then for E2, you substitute the charge, this charge, because E2 comes from the electric field by this charge, negative charge. So you substitute the value of 8 microcoulomb. So you get 7.19 times 10 to the 6 Newton per coulomb. Okay. Then from these two value, you use then you find the resultant electric field. So the resultant electric field, you can use resolution method. So you draw the triangle. You draw a parallel. You use parallelogram method because here is 90. Here is 90 degrees. Okay, given this is 90 degrees, so can straight away use a Pythagoras theorem. Okay, so E1 then E2, use Pythagoras theorem straight away because the angle here is 90 degrees, so this is a rectangle. Okay, so E equals to square root of E1 squared plus E2 squared. So substitute these two values and you get the resultant electric field is this way, okay, which is 7.41 times 10 to the power of 6 Newton per coulomb. Okay, so for the direction, you can use tangent, okay, the angle here, and tangent E1 per E2. So substitute these two values also and you get theta equals to 14.1 degrees, okay, to the line joining PB, to the PB lah, to the PB. Okay, so that's example. And then we try one more. If the point P is changed to here, okay, just now on top, so change to this position in the middle.